The third way of doing multiplication with vectors. We've talked about scalar multiplication, the idea of stretching a vector. We've talked about dot product, which is this scalar quantity that can tell you about the angle between the two vectors and can tell you the work done. The third one is the cross product. It is easily the most difficult one to get, but it also there are tricks and so on, and you'll have the memory aids and things with you. So, and don't forget to you also have GeoGebra to calculate it for you. Again, you need to know how to do it. The thinking question, for example, I'll be looking to see that you know how to do it. But of course, checking your work or working on other sections, you should know how to do it, but you should use GeoGebra to check your work at the same time. The cross product in physics, it mainly it has to do with torque, which we'll talk about, and it has to do with rotation and some stuff with electromagnetic fields. For us, we're mainly interested in what is it, where does it come from, how do you use it, and why do you use it. So let's start with what the cross product does. Let's make two random vectors. So we'll say A is 1, 2, 3, and we'll say B is 4, -2, and -1. When I take the cross product, so I type cross, okay, and then what does it want? It wants two vectors, right? Vector comma vector. So I'll do A comma B since both of those are vectors. It draws this third vector U. Now what is important about the vector U that it drew is that it is perpendicular. Okay, it's perpendicular to B, and it's also perpendicular to A. So it's like creating a third vector that is perpendicular to both of the two vectors that you started with. Okay, this is A cross B, and you can see the operation for cross. Many people use an X with a circle around it just as an alternative, so not to mix it up with multiplication. Let's cross B cross A and see that when you do B cross A, you get the same vector but pointed the opposite direction. So the first thing we want to realize about the cross product is, unlike the dot product, the order that you cross them in matters. So here you can see A cross B points up and B cross A points down. Now, some questions will ask you about what is the direction that the cross product is going. How do I know which one of these to take? The idea would be you use your right hand. You lay your right hand down flat on the page along vector A so that your fingers point in the direction of vector A. Now, vector A, if A is the first vector in the cross product. So like it's A cross B, you start with vector A. Put your fingers on vector A and then curl them towards vector B. Of course, you have to curl them across the angle between them, right? So you curl them the shorter distance towards A. You don't curl them like all the way around 360 towards B. You curl them in the short direction towards towards B. Okay? If you do that, your thumb will point in the direction of the cross product. So you can try it with this picture you can see right here. Lay your hand flat along vector A. Curl your fingers upward towards B, and you'll see that your thumb points back towards you or out of the page. On the other hand, if you have to line your fingers up with B and curl them towards A, your thumb is going to point into the page, and that's why we've defined that as a negative. We'll come back to this. It is a bit tricky, of course, as sort of visualizing in 3D and using your hand and so on. But for the time being, just understand that they do point in different directions. And if you get a question where you need to know what direction the cross product points, you refer back to this part and you work on, your right hand rule. Now, the magnitude of the cross product has a physical correlate, and that is that the magnitude of the cross product is equal to the area of the parallelogram that A and B create. So remember, A and B are two vectors that originate from the same location, and you can use them to construct a parallelogram. And the parallelogram would have an area defined by its base times its height. Now the base of this parallelogram is the magnitude of A. The height of this parallelogram is magnitude B times sine A, and therefore the area of the whole thing is AB sine theta. This is in contrast to yesterday where you had AB cos theta, which was the dot product, right? The cross product has a magnitude of AB sine theta. Now be careful. The cross product itself is not AB sine theta. This is only its magnitude. So if you want the length of the cross product vector, you can do AB sine theta. Let's demonstrate that here. So I'm going to do length of u is 16.88. Let's delete v because we don't really need it right now. So remember, u is the cross product. I'm going to do length, let's do angle between A and B. So the angle is 100 degrees. Now what I'm going to do is length A times length B times sine alpha. Okay, notice it gives me the same thing. Oops. It gives me, I see, the same thing as the length of u. Okay, so the magnitude of the cross product is the area of the parallelogram, or also AB sine theta. Okay, now of course you got to be a bit careful here because normally when you cross two vectors, your answer is also a vector, not a scalar. But if all you want is the length of that vector, you can use this AB sine theta thing. Suppose A and B are two non-collinear, non-zero vectors. Okay, why does it matter that they're non-collinear and non-zero? Of course, they can't be zero because any vector is perpendicular to zero. And they can't be collinear because if they're collinear, remember, collinear means parallel. How would the computer know what to draw if you wanted something that was perpendicular to two vectors that are collinear? Let's try the same project again, but this time let's make vector A 1, 1, 1 and vector B 2, 2, 2. Now A and B are clearly collinear because they're parallel, and collinear just means parallel, right? You can see that it follows the equation A equals 2B, right? 2A equals B, right? If you doubled A, you would get B. Now, watch what happens when I try to cross A and B, right? It doesn't know what to do. It just comes up with 0, 0, 0. And you might think about why that is because if I asked you to find a vector that's perpendicular to this one, to these two, there are too many answers. There are too many answers that are perpendicular to this vector. Let me draw them for you. Let's create a point, 2, 2, 2, at the end of this vector. Okay. Now let's make a circle at that point with a radius of 1 in the direction of A. Okay. So here's a circle that's floating in 3 space, and you can see that that circle is perpendicular to my vectors. Now, here's the tricky part. If you take a point on that circle, okay, so there's vector BA, for example. Okay. What's going to happen when I dot V, so let's dot product, okay, V and B. So V is the vector on my circle, B is the vector that, is in the question. When I dot them, I get 0. Remember, when you dot product two vectors, the answer is always 0 if they're perpendicular. That means that this vector I just drew is perpendicular. However, I can move B anywhere around this circle, right? And all of these vectors are perpendicular to the one I started with. So the problem here is actually that if you try to cross two vectors that are collinear, that are going in the same direction, there are too many answers because there are an infinite number of vectors, all the vectors that go around this circle, right, that would be perpendicular to the two that you have. So how could the cross product tell you what unique vector is perpendicular to your two vectors if there's an infinite number of answers, right? It can't do that. So that's why you cannot cross collinear vectors. You're just going to get 0, 0, 0. Of course, you can't cross zero vectors because every vector is perpendicular to 0. So the problem is it just generates too many answers. It doesn't know what to do. That being said, as long as the two vectors you created are not collinear and they're not 0, then you can always get a cross product. And the cross product has the special property that it is perpendicular to A and it is also perpendicular to B. Okay? A cross B, in my picture here, I'm going to say points up out of the page. B cross A, on the other hand, I'd have to put my hand upside down to do that, right? Yikes. I'd have to put my hand upside down, right? Like my thumb would have to point into the page in order to run my fingers along B and curl towards A. Points down into the page. Okay, so that's B cross A would point downward. Okay, the cross product gives you a vector. Another name for it is the vector product. This is in contrast to the scalar product from yesterday, which is also known as the dot product. Same thing. Scalar product or dot product are the same thing. Again, usually we just use cross and dot. We don't usually say vector and scalar, but if you come across it, you'll know what it means. The magnitude of A cross B is AB sine theta. A cross B is the opposite of B cross A. So B cross A and A cross B are very, very similar to each other. Just one of them is the negative version of the other. And again, we can sort of demonstrate that fairly simply if we just make up a vector A is 1, 1, 1, vector B is 2, 3, negative 7. And we cross A and B, and then we cross B and A, and you notice, negative 10, 9, 1 versus 10, negative 9, negative 1, right? It's the exact same vector. It's just all the components have become the opposite sign of what they were the first time. So that's what this third one is saying. Okay, two non-zero vectors are collinear if A cross B is 0. Really important. Yesterday, I gave you a test for how to test if two vectors are perpendicular. To test if two vectors are perpendicular, check their dot product. If their dot product is 0, they have to be perpendicular. Today, if you cross two vectors and get 0, you must be collinear. Okay, so this is a different test, how to test if things are parallel. So you can test that things are parallel by checking if they have a cross product, of 0. Now, mind you, many times it is often easier to test if vectors are collinear by checking if they are scalar multiples of one another, i.e., vector u equals kv, right? If u equals kv, they are collinear. But if u equals kv, you would also have the case that u vec cross v vec equals 0. Okay, that would also be the same thing. Like they're two. If you know one, you automatically know the other. Okay, so this is useful to know, but often it's easier to just use what you already know to check if things are parallel. Just check if they're scalar multiples of each other. Okay, if you have a scalar number and you scale u before crossing with v, it would be the same thing as scaling up the cross product or scaling up v and then having u cross with that scaled up v. Okay, so basically you can put the k wherever you want. Again, this is a really interesting one to try to prove. I think this would be a really interesting one to try, see if you can explain why this one works. But This basically says if you cross u with the sum of v and w, it would be equal to u cross v plus u cross w. Try to prove that one. I think would be a really neat task. I'd love to see someone post on the web page a proof of why this works. All right. If you cross a vector with itself, you just get 0. Okay, because you get magnitude I times sine 0. Sine 0 is 0, so you just get 0. Right? So if you try to cross a vector with itself, you're always going to get 0. And again, we can just demonstrate that quickly by doing A cross AA, and we get the 0 vector. I should actually specify that. It's not just 0, it's rather the 0 vector. So it's not a scalar, right? I don't actually like what they've written up here. I don't think this is useful. If you cross I, your answer is the 0 vector. If you want the magnitude, right, of I know this is painful to watch, but I want to make sure all the symbols are right. If you cross a vector with itself and check its magnitude, you just get 0. If you cross a vector with itself, you get the 0 vector. Now, of course, these things are very similar to one another. They're not quite the same thing. This is a scalar, this is a vector, right? Okay, j cross j and k cross k is also the 0 vector. If you cross I and j, okay, you get k. If you cross I and j, you get a vector of magnitude 1 in the direction of k. Again, that shouldn't be too hard to understand. Let's just do a quick example of the 3D graphics here. So let's draw a vector I, vector j. Now, what would be a vector perpendicular to those two? Start at the red, so point your fingers directly up right now. Like, curl them towards your left. Your thumb is going to point towards you. Okay, and that's the positive in the direction of z, right? So let me just right. So if I go cross ij, it's going to give me a vector k. I'm just going to rename it to k, right? That points straight upward. Now, on the other hand, if I start with the j first, if I cross j and then do I, it's going to point down. It's going to be negative k. Okay, so you can see there that one's pointing downward. Okay, so again, j cross I is negative, j cross k is positive, k cross j is negative, k cross I is positive, I cross k. Again, like, do you need to memorize this? No, just use GeoGebra to check it, or use the right-hand rule, right? Again, this is all pretty easy. All you have to do is just put in I is 1, 0, 0, j is 0, 1, 0, k is 0, 0, 1, and then you can just use GeoGebra to check these things pretty easily. Now, like yesterday, we want to figure out a way to get the cross product. Not just know its magnitude, but how do you actually find it? Now, one definition is to follow this this pattern, but I'm just going to ignore this. It's not a bad way of doing it. No problem if you want to go through it. I'm going to teach you how to do it according to this shorthand. I think is more useful. This is how you calculate the cross product. I'll briefly talk about this for those of you interested in the future. This symbol here is called the determinant of a matrix. This is a matrix. A matrix is just a list of a two-dimensional list of numbers. So you have number 1, number 2, number 3, number 4. And the determinant is to make an X pattern where you go AD, take away BC. So you do a series of determinants, and that's what tells you how to get the cross product. That's a good way of doing it, but I'm going to show you a way of doing it that I think you'll find a little easier. Let's say we are trying to cross A with B. What you do is you take the vector A and you write its components out like this. the second component, the third component, the first component, and then the second component again. Okay? Underneath that, you write the same pattern for B. Third component, first component, second component. Okay? Exactly like that. Just write them right on top of one another. I'm going to just make a little bit of, sorry, it doesn't actually need a comma. I wasn't really thinking. Spread them out a bit. Okay? So you just write them out in that pattern. So basically you start at number 2, and then you count upwards, you loop back to number 1, and then you just end at number 2. Now, the cross product, so A cross B equals A2 B3 minus A3 B2. So basically what you do is you make a little X here, and I'm going to just use the picture that they have because it's perfectly good. 1 times negative 3, take away negative 1 times 2. That's your first component. Negative 1 times 1, take away 2 times negative 3. That's your second component. 2 times 2, take away 1 times 1. That's your third component. So again, let's just go through this together. So hopefully you have these written down. So what we do here is we write out, so 1, negative 1, 2, and then 1 again. For the bottom equation, 2, negative 3, 1, and then 2 again. Now my cross product is equal to 1, so I start in the top left, 1 times negative 3, take away negative 1 times 2. That's the first component of my cross product, so I put a comma. Now I move 1 unit to the right. I do negative 1 times 1, take away 2 times negative 3. That's my second component. My final component is the 2 times 2, take away 1 times 1. Okay, and that's going to be what I get here. So let's just go through and answer it. So negative 3 plus 2, comma, negative 1 plus 6, and then 4 take away 1. So this is negative 1, positive 5, and 3. And this is equal to A. I'm going to ignore the vector signs, but it should have vector signs. A cross B is negative 1, 5, and 3. How do I know if I did this right? Because that's a lot of little steps, right? It should be the case that A dot A cross B, right, should have an answer, yikes, should be 0, right? Because think about it. The cross product A cross B gives you a new vector perpendicular to both of the ones you started with, which means if you dot the one you started with the new one, it should give you 0 for both of them, right? So let's try dotting 2, 1, negative 1. Let's dot product that with our answer, 1, negative 1, 5, 3. If you dot product this, you get 2 times negative 1 plus 1 times 5 plus negative 1 times 3. This gives you negative 2 plus 5 take away 3, which gives you 0. Pretty sure I did this right. Let's go ahead and dot with B. 1, 2, negative 3. Okay, we're going to dot with our answer, negative 1, 5, 3. What happens when we dot these together? 1 times negative 1 is negative 1, plus 2 times 5 is 10, plus 3 times negative 3 is negative 9. So we get 10 take away 10, which is also 0. So I know I did this right. The cross product here is negative 1, 5, and 3. Again, how do you do this? You just follow the setup here. Okay, so start with the second component, then the third, then the first, then the second again, and you do this sequence of 3 x's where you subtract, you multiply these two, and then multiply these two, and then subtract. Okay? All right, let's try another one. It says if u is 4I plus 3j take away 2k, and v is negative I plus 3j plus 2k, find u cross v. All right. So let's first things first, let's get it out of this sum form and write it in regular component form. U is 4, 3, negative 2. V is negative 1, 3, 2. Okay, now I want to cross them. So to cross them, I'm going to start with u, because that's the first one. So 3 space 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 negative 2 space 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 4 space 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 3. Okay, so all I'm doing there is just writing out the components for vector u starting with the second one. Here's the same thing with vector v. 3, 2, negative 1, 3 again. Now these don't line up quite right because the negative signs are really big, but hopefully you get the idea. U cross v, whatever, the cross thing's right up there. Okay, is equal to, again, draw the vector signs, please. I'm just trying to save us time by not writing them, but you do need to write them. U cross v, okay, would be, so I start with the 3 times 2 is 6, take away negative 2 times 3, which is negative 6. Okay? Then I move to the second set of x's. Negative 2 times negative 1 is positive 2. Take away 4 times 2 is 8. Then I move to the third x. 4 times 3 is 12. Take away 3 times negative 1 is subtracting negative 3. Okay? So u cross v is equal to 12, comma, negative 6, comma, 15. Okay, again, let's use GeoGebra to check rather than manually checking, but it's not that hard to manually check. You just dot product them, right? Okay, so here we go. U is 4, 3, negative 2. V is negative 1, 3, 2. I'm going to cross U and V. I get 12, negative 6, 15, right? So there's the cross product. Perfect. Okay, and you can see again, what did it do? It generated a new vector that's perpendicular to the 2 that I started with. Okay, now, okay, this one's a long one. If u is this, and v is this, and w is this, find. Okay, the triple scalar product, u cross v dot w. The triple vector product, u cross v, and then cross with w. All right. Just looking ahead to see what we've got left here, but I think I'm going to do A, but I'm not going to do B. I'll show you how you would do B, but I just think for time, I don't know how many cross products you want to watch me do here, but I think it's enough. So let's do U cross V. We need to do U cross V for both questions, right? So 2, 1, negative 1, 2. Underneath, I'm going to write V, negative 1, negative 1, 1, negative 1. Okay, let's cross them. 2 times negative 1 is negative 2. Take away negative 1 is negative 2 plus 1. We go into the middle one. 1 times 1 is 1. Take away 1 is 0. Third one, positive 1. Take away positive 2 is negative 1. So we end up with this vector negative 1, 0, negative 1. Again, a quick check of this should help to determine if this is perpendicular. So negative 1 times negative 1 is 1. 2 times 0 is 0. 1 times negative 1 is negative 1. If you add up all those numbers, you get 0. That's good. And the same thing would be true here because it's the same thing, just kind of flipped. Okay, so here's my U cross V. Now I'm supposed to dot this with W. So negative 1, 0, negative 1. Oh, sorry. And I'm supposed to dot this with W. W is 1, 1, negative 2. If you dot these together, you get negative 1 plus 0 plus 2, which is just equal to the number 1. Okay, again, let's just do a very quick check and make sure I didn't make any mistakes there, but I think it's probably good. Negative 1, 2, 1. V is 1, negative 1, negative 1. W is 1, 1, negative 2. And then let's say UV equals cross UV. And then let's go dot UVW, and we get the answer 1. Okay? Now for the second question, all you would do, take my same answer for U cross V, right? And then instead of dotting it with this, cross it with that. And just repeat the cross product procedure. We're going to have to do a number more cross products today. I think this is just practice, so you go ahead and do that on your own. Okay, if magnitude of u is 4, magnitude of v is 10, and the angle between u and v is 30, find the magnitude of u cross v. Okay, well, again, this is a very, very easy question because the magnitude of u cross v is simply equal to the magnitude of v times the magnitude of u times sine of the angle between them. And the angle between them, remember, we use theta as customary. Now, VU sine theta, 4 times 10 times 0.5. Sine 30 is 0.5. So 4 times 10 is 40, times 0.5 is 20. The area of the magnitude of the cross product is 20. Okay, so that's that. Pretty straightforward. Just making sure you know the formula. You could check your work here by drawing it and getting the area of the parallelogram, but I don't think we need to. Okay, this is a very, very, very common question. Guaranteed to get this in communication. State whether each of the following expressions has meaning. If not, explain why. If so, state whether you would get a vector or a scalar. All right. In the first question, you are so look at the brackets. You have to cross these two first. When you cross those two, you get a vector. Then it's asking you to dot your new vector with an old vector u. Okay? Yes, this has meaning, and the ultimate answer would be a scalar, because basically what's happening is you're dotting two vectors together, and we know that when you dot two vectors together, you get a scalar. Wow, I have no clue how this has been formatted. I will be back after I've turned this into a table. Okay, again, this one here is a scalar because you're crossing two vectors and then dotting them with a third vector. This is meaningless. You are trying to cross two scalars. You can't do that. You can't cross product two scalars, right? Think about what's happening here. U dots with V and becomes a scalar. Okay, then you're trying to cross that scalar with another scalar. Doesn't do anything, right? Here, you're trying to add two vectors together. When you add two vectors together, they equal another vector. That vector can cross with another one, sure. Yes, this works. The answer would be a vector, because when you cross two vectors together, you get a vector as an answer. This is meaningless. You cannot cross a scalar. And we know that when you dot v and w, you're going to get a scalar, and then you're trying to cross that. It doesn't work. Again, this one is kind of open to debate. I'm going to say it's meaningless because you can't dot scalars. I mean, it might actually do something. Let's make up a number. A equals 3, B equals 6, and then dot AB. It probably just multiplies them. But to me, I think based on what we're learning here, I just wouldn't. I mean, at least in a vector sense, this doesn't really mean anything. I guess you could say, could be just regular multiplication. I guess, but like, what does that really have to do with our unit? I wouldn't worry about it. Same thing might actually be true here. Let me just try this cross AB. Yeah, okay, that it actually can't do. So that one is meaningless. This one you could say this is the regular multiplication of two numbers, but you're using the dot there in the sense of multiply, not in the sense of dot product. So I think I would just say this has no meaning. That's fine. This exists. This is a vector. It's just scalar multiplication. Okay, so yes, this exists. So I always ask this question. I want you to think about this. I'm not going to give you exactly the same things you see here. And I want you to not only think about whether it exists or not, but if it exists, what might it mean? Right? What might it be significant? What might be significant about it? So like, for example, in this third one, you could tell me, yes, this exists. It's a vector, and it's a vector that's parallel to vector v. Okay. This triple scalar product, we don't know what this means yet, but we will get there. So when we get there, you'll know what to do with that one. This one, all you'd have to do is say something like, this will give you a new vector that is perpendicular to u, as well as perpendicular to v, as well as perpendicular to w. Sorry, let me correct what I just said. It wouldn't be perpendicular necessarily to v or w. It would be perpendicular to the sum of v and w. Sorry, just forgot my order of operations there. Okay, anyway, get rid of all this. Okay, find a unit vector perpendicular to u and v. All right, this is a very good question. Okay, again, this is the kind of thing, it's easy to forget. We learned a lot of stuff, and people forget what a unit vector is. So let's review. First of all, to find a vector perpendicular to both of these, I will use the cross product. So let's start with that. Let's take the cross product. So u is easy. 1, 1, 1, 1. Simple. For v, -1 first, -2, +2, and then -1 again. Okay, how do I actually cross product these? I'm just going to say it as I do it in my head. -2 take away -1, +2 take away -2, and -1 take away actual 2. Okay, so I get that. Again, a quick check is probably worthwhile whenever you do a cross product, just to save yourself the pain of making an error. So if I draw 1, 1, 1 is u, and then v is -1. Sorry, wait, what was 2, 3? Oh, sorry, started with. I should just move it so I can see it. 2, -1, -2. Okay. Now I suggested when you cross these two, I get -1, +4, -3. Okay, so we're on track. Now, so let's define w vector as that. What I want to know now is w hat. What is w hat? W hat, or the unit vector in the direction of w, has to point the same way, so it has to be a scalar multiple, but it has to have a magnitude of 1. Okay, the magnitude of w hat has to be 1, and I also know that w is equal to kw because they're in the same direction, right? It must be the case that k, they go in the same direction, so they're scalar multiples of each other. K, I also know, has to be equal to 1 over the magnitude of w itself. So here's why writing all these little symbols and hats and arrows is important, because when you get to a question like this, if you've been ignoring that stuff, it's gonna cost you in this kind of thing, because you're not gonna know what any of this stuff means. It's gonna take you too long to go back and review it, right? So think this through. A unit vector in the direction of w has to go the same way w does, which means they have to be scalar multiples of one another. We also know that you have to scale down its magnitude to basically divide out its magnitude to get a magnitude of 1. So, final thing to say here is equal to vector w, vec w, divided by its own magnitude. Okay, and that is really important. We've talked about this already, but we haven't needed it really in a question. So this is all you got to do. So here we go. Again, it's not that hard to do once you know what you're looking for. the magnitude of vector w is pretty easy. It would be the square root of 1, negative 1, I guess I'll do it this way, negative 1 squared plus 4 squared plus negative 3 squared. Okay, and we know that that is equal to the square root of 1 plus 16 plus 9 is 26. Okay, so how do I now write the unit vector for w? So w hat would be equal to, okay, so this is how you do it. You write out the vector the same way it was, negative 4, negative 1, sorry, 4, negative 3, but underneath each one, you divide each component by the magnitude. Okay, and I will just show a quick demonstration of this and we'll call it a day. If I could ever copy paste what I'm trying to. Okay, this would be a unit vector in the direction of w. Okay, all you got to do is find the magnitude and divide each component by that magnitude. Let's make sure I did this right. So here's vector w, right? It's perpendicular to the 2 that I had, so that's right. We did the cross product. Now, what if I want to take vector w and I want to go 1 divided by square root 26 times w? Okay, you see it draws a small vector in the same direction as w, but if I type the length of a, it gives me a length of 1, and not just close to 1, but actually 1, right? It gives me a vector in the same direction as w, but with a magnitude of only 1. Again, I'm stressing this point because many people forget how to do unit vectors and it costs them on the test. So don't forget. Make sure, even if you just want to put it beside your notes something, just like, quickly, how to do a unit vector, what a unit vector means, right? So again, this is not a difficult question. You should be able to get this one, but if you don't know any of these unit vectors or magnitudes or whatever, it's easy to get lost.